Elisa Chalouhi, and I just finished my PhD in KTH. And the topic of the PhD is optimal design solutions for road bridges considering embedded environmental impact and cost. So the problems that we're facing right now, and I guess you're aware of it, is that we have this growing population and an increasing amount of this population living in urban areas, which means that we need to build over and over more bridges and more infrastructures, and we need to do it in a limited amount of time and try to follow pretty conservative design codes, which makes our designer lately try to prefer simplified solutions. All of these will lead to the need of producing a lot of material, and we're talking about concrete, cement, reinforcement, etc., which are materials that are responsible for a lot of our emissions of CO2, for example, and they also represent a significant economical burden for our society. So we have two problems, emissions and cost. But how are we design our structures to consider these problems? And this is the simplification of a typical design approach, which is called a point-based design. So our engineers start from a model based on their own experience, perform structural analysis or the steps that you know, and then they perform cross-sectional verification. So they look for functionality of a structure. And that is the only criteria. So usually, once functionality is reached, or directly from the initial model, or with simple simplifications, with simple modifications of the model, we stop here. Unless there is nothing we can do, our initial model was too bad, and then we can create a new one. But usually this is quite seldom done. So if we look at this process, we never consider cost and environmental impact in the design. So how are we supposed to affect them if we only calculate them after the design process? And that is why I'm proposing this alternative design approach, which follows the same steps up to the functionality check, but then I think we should actually calculate cost and environmental impact associated to our structure, and we shouldn't stop here. The only way to reduce these quantities is to actually compare different solutions. So start over, new model, a better one, and keep learning and learning and learning until we can stop, analyze all the solutions that we looked, and pick the best one. This, of course, requires automation, which is a problem, we know. But let's say that we have automation in place, then this that I'm showing here is nothing but a concept of structural optimization. And structural optimization is nothing new, at least not in the research field. When it comes to bridges, we've been studying structural optimization since 1970, so it's more than 50 years, and still is not applied on a daily basis in our offices. There are a lot of reasons for this. Business model is one of them. But if we look at what research did wrong, the main problem that researchers found is that usually optimal solutions tend not to be feasible. They tend to be too complex to be built. And what is the problem there is that most of them focus only on material cost. So they make this structure with weird shapes and super slender, impossible to be built. Or they oversimplify the structure. So they oversimplify the structure, they oversimplify the loads, they oversimplify verification. In the end, what we optimize is no more a bridge. So what I did in my work was trying to come up with an approach that would reduce these quantities while still produce feasible solutions. And solutions that fulfill all Eurocode requirements, Trafikverket requirements, and so on. I applied it in 3 different structures. Today I'm going to show you 2 out of 3. And then I also try to understand how cost-effective and climate-friendly solutions relate to each other, and what is the role of every different materials, since we always speak about concrete and cement, like the bad guys of the situation, but is it the case? What is the role of reinforcement? And then one problem is that we don't have automation in today's offices, at least not in all of them. So designers have to use a point-based design approach. So I try to come up with some recommendations so that at least the original model is not based only on the experience of the designers, but also on some optimization calculations. So let's jump into the first application, reinforced concrete road beam bridges. So this is what the static system looks like, or can be systematically modeled as. So a continuous multi-span beam over several piers with different type of connections between superstructure and substructure. And this is what instead the cross-section would look like. We're talking about full concrete with reinforcement made of traditional steel. What I tried to do here was optimizing the entire structure without simplifications, starting from the optimization of a static system, so number of spans, location of the piers, and connection between superstructure and substructure. Once that is optimized, I went into the optimization of a superstructure, trying to find all the optimal dimensions that you see listed here, and at the same time designing in a detailed way their reinforcement. And the aim of this is trying to minimize investment cost and environmental impact. Investment cost of the entire structure, considering all the main materials involved, but what is important here is that I consider both material cost and labor cost. And labor cost, it is proportional to the quantity of material. If you pour 1 cubic meter of concrete, it takes half than if you pour 2 of them. But there are other things we need to consider. We need to consider the material we're looking at. Is concrete, is reinforcement, is steel reinforcement, is GFRP, all of this. But also and especially where we are pouring it, where we are installing it, what is the shape of this element, what is the location of this element. All these things need to be somehow quantified if we want a solution that is not only optimal on paper. And the other things that I'm trying to minimize is environmental impact, again, of the entire structure with all the included materials, and considering not only CO2. Here I did a bit of a wider analysis. I consider also other 2 types of pollutants. This is one of the case studies that I have. It's an existing bridge designed by Elu Consult in 2017, I think. This is what the static system looks like. This is the cross-section, and it has a constant cantilever all along the deck, constant inclination, and varying height of the superstructure. So I try to apply my methodology to redesign it. And in this graph you see on the x-axis the number of generations. If you remember that cyclic method that I showed you before, this is how many times I do the cycle. On the y-axis, we have a list of normalized quantities, which are all of these. In other words, amount of materials involved, what I'm minimizing, environmental impact, and the corresponding cost. So here I was not trying to minimize the cost. I was only trying to minimize, let's say, CO2. Now, if we focus on the red line, which is the one for the environmental impact, as expected, is decreasing, because that's what I'm asking my method to do. But then if we look at the corresponding cost, this is decreasing as well. So I wanted to show you this slide because there is a misconception that climate-friendly solution will necessarily be more expensive, which is not the case. Not when we talk about reinforced concrete structures, not when we talk about structural optimization. If we're comparing different types of bridges, it might be. But when we try to find what are the best dimensions for the solution, then they really move together. But now, what does the solution looks like compared to the existing one? And in here I show you in red the build solution, the existing bridge, and in blue what I call the buildable optimal solution. So I run my program, I get an optimal solution, and then I'm a structural engineer myself, so I look at the solution, I use my judgment, I tweak it a bit, modify it a bit to make it more buildable, and see if I can still obtain some savings. And this is what it looks like. So up here you have the static system. As you can see, in both cases, build and optimal is symmetric. In both cases, it has 5 span, so actually the built one is a suboptimal solution. When it comes to the cross-section, here you have half of it because it's symmetric. We have again constant cantilever, constant inclination, but notice that the optimal inclination is pretty different because you don't need material down here. And the only difference really is that the build solution has 2 different heights that you can see here, and then linear interpolation between them. What I'm proposing is let's add a tiny bit of complexity. Let's add the 3rd height, because it seems like in these 2 span we don't need so much material. So let's add that, and by doing this we have savings of 10% in cost and 13% in environmental impact, which might seem little, but let's consider the dimension of this bridge. So it's not that little if we manage to save these amounts. So this is for the case study. Now I try to draw recommendations for designers. This is one of them. So I try to study different total length of the bridge, the x-axis, and again, minimizing once the environmental impact, once the investment cost. And I try to study different number of spans. So if I put together the results of these 2 graphs, once again, they agree with each other, so I can come up with just one table that tell the designers, if you need a certain length, let's say 60 meters long bridge, then you should go for 4 span if you want to minimize cost and environmental impact. Now, second application, I'm talking about reinforced concrete overhang bridge slabs, so the part within the dotted line in these 2 examples, that can be isolated and studied as a taper slab, clamped on one side, free on the other side where we have edge beam. Now, this length, the cantilever length, usually depends on the design in the longitudinal direction, so we assume that it's fixed. And what I'm doing here is trying to optimize the thicknesses of the slab and the height of edge beam, while again designing the reinforcement. And in here I consider 2 types of reinforcement, traditional steel, but also GFRP. And the reason for this is that these elements tend to have quite high maintenance due to the reinforcement that has problem with corrosion. So I'm proposing a reinforcement GFRP which doesn't have this type of issues. Again, what am I minimizing? Investment costs, and this time I add another type of cost, which is cost for life cycle measures. So all these activities that we need to perform throughout the life cycle of a structure to keep serviceability. In this specific case, when we look at steel reinforcement, again, we have a problem with corrosion, so we need, for example, to replace the edge beam, to impregnate the edge beam, everything that is about taking care of the corrosion. And these type of activities are not needed when it comes to GFRP. So this is the entire thing I'm trying to minimize, and I'm also trying to minimize the environmental impact. In this case, I made it simpler. I only look at CO2, so I only look at global warming potential. Again, same case study, so we'll just skip over this slide, and I try to optimize alone this component. And here you see a lot of results. What you need to look at is, this column is what minimizes both cost and environmental impact using steel. And here instead we have minimizing CO2 using GFRP, minimizing cost using GFRP. So one thing, using optimization, no matter the material, reduces of a certain percentage everything, not only actually cost and environmental impact, but also weight. And this is an issue, because this type of element doesn't have a big impact in the resistance of the cross-section in the longitudinal direction. So usually they design it based on rule of thumbs. But this element has a weight, and the weight is part of a self-weight, is part of a design of a superstructure, which then is part of a design of a substructure. So over-dimensioning of, for example, what is it here? 14% the weight will over-dimension all the rest. So it is a bit of a domino effect. Another thing to notice here is GFRP versus steel. So not only optimization helps us, but GFRP, we expected it to have a lower life cycle cost because it's more durable. But another misconception, these new materials are more expensive. Well, not really, because even cost is a tiny bit lower compared to the steel cost. And environmental impact is crazily lower, it's 20% less, 30% less compared to the existing solution. Again, some recommendations for designers. Here I'm trying to vary the cantilever length on the x-axis, and then trying to find what is the optimal thickness in the case of GFRP reinforcement and steel reinforcement. When it comes to the edge beam height, you never see it cited, because one thing that happens is that no matter the case I'm looking at, no matter the reinforcement, no matter what I'm minimizing, is always 40 centimeter tall, which is the minimum allowed by Trafikverket. And when I tried to remove this limitation from my optimization, it was completely getting rid of the edge beam. So that's another bell that should ring, and we should say, okay, do we really need it? Or yeah, we do need it, but can we replace it with something, I don't know, more climate friendly, more less expensive, less high maintenance? Now, going back to this graph, so given the cantilever length, if you know the material, you can enter in your length and you can find what are the best thicknesses for your slab if you want to minimize or cost or environmental impact. If you can choose the material, then I show you this graph, which again has cantilever length in the x-axis and CO2 emissions on the y-axis, and it compares steel case with GFRP case. No matter the cantilever length, GFRP wins all the time. And it's the same with cost. It's less strong, the difference, but it's the same. So if you can choose, go for GFRP. The only thing is that GFRP, as you can see here, tends to want a thicker slab. So we save less in weight, but we save a lot more in environmental impact. One last thing, whenever we have two different solutions, we see some patterns. So climate-friendly solution have less concrete. Cost-effective solution has less steel. So we'll try to go quickly through this slide, but I think it's really important. So here we see, given 1 cubic meter of material, what is the cost, like the relationship between cost of reinforcement and concrete, and the relationship between CO2 emissions. It seems like the reinforcement is always the bad guy. But then we remember, it's reinforced concrete. So in 1 cubic meter of concrete, we have a super tiny amount of reinforcement. We have between 1 and 4% for steel, and 1 and 3.5% for GFRP. So if we put together all this information in this graph, that has nothing to do with optimization, like any company can do it today, as long as you know what is the reinforcement content that you're allowed to use, and as long as you know these values, then you can create this graph that has on the y-axis the ratio between CO2 emissions of reinforcement over CO2 emission of concrete, or cost of reinforcement over cost of concrete. And if we look at this curve, for example, is the one for GFRP when I look at CO2 emissions. So what I'm saying is that it's always below 1. So the CO2 emissions of reinforcement are always way lower, no matter how much reinforcement I'm putting in, than the one of concrete. So if I want to effectively reduce my total emissions, what should I do? Try to reduce the amount of concrete. But when I look at cost, same material, the things changes, because if I am above, what is this, like 1.3, 1.4% content, then is always that the cost of steel is higher than the cost of reinforcement is higher than the cost of concrete. So if you want to reduce the concrete, you should reduce the reinforcement amount. So, when we look at steel reinforcement, the two curves coincide. That's why we always get the same solution. That's why we shouldn't worry of having a climate-friendly solution. But this graph, I think, is important because today we know how much reinforcement we use, whatever the reinforcement is. So instead of saying, let's just reduce concrete all the time, let's check in this type of graphs, where do we end up? Do we end up here, which is quite common, for example, for steel reinforced structure, or do we end up down here? Because we might be doing something that is actually worse for our structure. So to draw some conclusions, it is possible to have optimal solution. It's not true that they're not going to be buildable. We just need to include some considerations on workability, etc. And when it comes to reinforced concrete structures with steel reinforcement, as long as we have today's prices and today's emission, cost and environmental impact behave the same. So we should really try to reduce one of the two and the other one will follow. And another thing, a lot of talk about cement and concrete being bad for the environment, and that's true on a mixture level. On a design level, though, it seems like is reinforcement the thing that is a bit problematic. So we should try to push our designers not to oversimplify, but to actually design using methods that minimize the reinforcement. We should try to use more recycled steel within our reinforcement. And we should also invest a bit, not only in the research to, replace cement, but also how can we get better climate-friendly steel reinforcement. And if we can't, or in parallel, we should try more durable and less impacting materials, such as GFRP. Last thing, which has been criticized a bit in my work, is like, but what about aesthetics of bridges? And I think we should change a bit the idea of aesthetics. So for example, what I showed you here, and it appears also in my work, is that we need to go for taller cross-sections, unless we have problems of minimum vertical clearance, but otherwise we need to do that. We need to allow a tiny bit more variations in the dimensions. Add one cross-section in a five-span bridge and you save 10%. And we need to look at those parts that are designed with rule of thumbs, like the cantilever, and try to reduce their dimensions. So thank you. Sorry for the long presentation.
Thank you. Let's see what we have. Do you want to check the...
Yes. Oh, okay.
You can choose...
a new presentation.
Okay, is pre-stressing included in my study? No. I only consider normal reinforcement. I consider also composite bridges, but that was not presented here because it was not the scope. Are the results from this research available where? Yes, they are available in my thesis that you can find on DIVA. If you just Google my name and then DIVA, you will find it there. Let's see, maintenance and demolition, etc. No, I don't consider that, and there is a reason, because here I'm working with size optimization. So usually if the bridge is, like, let's say if the cantilever is thicker or thinner, that won't change so much in terms of demolition, in terms of maintenance. It does when you compare different type of structures or different type of materials, for example, GFRP versus steel. But if you optimize, like you decide you want steel reinforcement, then that doesn't really add any value. So that's why it has not been included. What was the most interesting thing you found in your work? I think that graph that I showed you, the most interesting is the most useful, because I'm aware, I work right now as an automation developer in a company to try to create these automated softwares that will design our bridges. But I know it's something new. I know that 99% of the companies don't have that in place. So, and if you don't have automation, you won't be able to use optimization. So we need to find alternative ways. And I think that graph and understanding how materials behave one with respect to each other and with respect to what you want to minimize, that's important. So that for me is the most interesting thing today of my work.
Thank you very much.
Thank you.
En satsning som vi gör här i Slite, den kommer vara nödvändig för att samhällsbyggnadssektorn ska kunna bygga fullt ut klimatneutralt. Det är ett stort omställningsprojekt. Vi ska i princip bygga nästintill en ny fabrik till fabriken för att kunna omhänderta uppemot 1,8 miljoner ton koldioxid varje år.